I've been thinking about sorting lately. I don't know really why, but I've been thinking about it, and I've been reading a bit about it because I have a couple of books that I'll recommend at the end that talk about it, and I think it's a really interesting topic, and I think it is at the very sort of inception of computers, and actually it's something that I didn't really thought about before, is that the word in Spanish for computer is ordenador, which literally means sorting machine, and that's something that I just never really thought about. Like, I used the word before, but I don't know, it just blew my mind slightly. So yeah, a bit of history. I found this really interesting. In 1980, it took the US government 8 years to tabulate all the data for the census for the population, and yeah, that should be 1890, not 1990. So the 8 years, so just in time for the next one. So they had to start all over again. So this guy, Herman Hollerith, invented a machine taking sort of inspiration from hole punch cards that they use for train tickets. And it was essentially, if you translated the data for the census into hole punch cards, then that machine would sort them. And he called that machine the Hollerith machine, not very original with his naming. And then that machine was patented, and that was like a massive hit. And by 1911, they founded a company called Computer Tabulation Recording Company. Horrible name for a company, but later they renamed that company to IBM. So yes, it comes from there. I don't know, I thought that was quite interesting. So now, sorting, the importance of sorting. Why is sorting so important in computer science, in programming? How many apps on your phone just consist of just an ordered list of things? Like Spotify is an ordered list of songs, and your email application is just an ordered list of emails. Just Slack is an ordered list of messages, just everything. And if you're doing any React is just about like mapping over data and just rendering it on the screen. So another interesting thing is that Google gets a lot of credit for their searching capabilities, but the thing that enables that fast search is good sorting of data. So keep that in mind, because I'll ask you later about this. So why is sorting so hard? This is really interesting. Sorting is very counterintuitive because it involves diseconomies of scale. So an example of economy of scale is that it's easier to cook for 4 people than to cook 4 separate plates for 4 individuals. A diseconomy of scale is that sorting 100 books is a lot harder than sorting 2 piles of 50 books. So keep that in mind, because that explains why the more the size of the input to a sort operation increases, the more complicated it is. So how do we measure how complicated it is to do something? So I'm going to sort of be plowing through probably like 2 years of computer science in university, but I'll do my best. So I'm getting into, someone might heard of big O notation in terms of measuring the complexity of algorithms. So I'm going to be talking about that at a very simplified way. So algorithm complexity, where essentially what it does is it charts the size of the input to a problem to the complexity of it. So some examples of that. So let's say that I'm doing a dinner party at my place. So cleaning my house for that party, it's a constant complexity, because it doesn't matter how many guests are coming to my house, I just need to clean my house. So it doesn't matter if I have 1 million guests or 2 guests, I still need to clean my house. Now, greeting every guest at my party has a linear complexity, because if I have 1 more guest, I have to greet 1 more person. So the complexity, the first one, if we graph that in a xy chart, would be a straight line, horizontal line. Now, the second one would be linear. That would be just a line increasing linearly. Let's call it sort of like 45 degrees. Now, if I made each of my guests greet each of the other guests, that would be an exponential complexity, because if I have 2 guests, then they only have to greet each other. But if I have 3, then each guest has to greet the other 2, and then that sort of doubles every single time. And that would be a curve going up. And there are more complicated things, like instead of n squared, you could have 2 to the n power, which is like a crazy graph that goes just up, straight up. And also you can have factorial, which is like the most ridiculous one. So I sort of hoped that I would have like my favorite whiteboard here, but it wasn't here. So I was going to draw them, but then I did realize that. So what is the worst way imaginable to sort a deck of cards? So if I wanted to sort a deck of cards, who can tell me the absolute worst way to do that? Yes, that is exactly, that is absolutely the worst way. Correct answer. So if I just throw that deck of cards up in the air and just hope that they land in the right order, that would be absolutely the worst way of sorting that deck. It could happen, right? It could happen. And if it did happen, the complexity of that algorithm would be constant because it doesn't matter how big the deck of cards is. I just throw it in the air, falls in the same order, and great, job done, right? But it doesn't happen like that. And actually, I learned something new. The odds of that happening are 8, and I don't even know how to pronounce that word, but that is an 80 with 66 zeros after it. And then I sort of thought that that would make the chances of winning the lottery while getting struck by lightning feel like winning a coin toss. Don't quote me on those numbers. You can probably calculate it, but I didn't. But yeah, it's just a huge number. It won't happen, but it could happen. So yeah, the complexity of that algorithm of just throwing the cards in the air and hoping that they will land on the right order. The reason that number is like the different combinations of unshuffled decks that you can have. So that is why, yeah, just a huge number. It doesn't matter. So this is the fun part of the talk. Gonna need some volunteers because we're gonna sort stuff. So yeah, volunteers. Who wants to? I need like 8 people. Yes, 1. Yes. Yes. Do you want to come? Zoe, do you want to come? I need someone tall too. So I need someone tall. I see a lot of people of the same height. Yeah, someone tall. Yes, you 2 guys are tall. Yes, come. 1, 2, 3, 4, 5, 6, 7. One more. One more? Yes, great. Thank you. So thank you to my volunteers. So can we just pretend that you guys are an array? Yeah? And the only operation that I sort of need automatic is like shuffling. Like you're already shuffled, but yeah, if I say shuffle, just shuffle and just be in a line and yeah, great. So, so yeah, let's go through the first algorithm. How can we sort data? And like the first question is like, well, what's the criteria? What do we sort people by? We could go by, I don't know, grumpiness, level of grumpiness, or like how long have I known them. But let's go by height because it's just the easiest, right? So the first one, selection sort. So this one, I put there sort of the pseudocode for these algorithms so that we, so that we know that you already can understand this algorithm. Even though I'm talking about complex algorithms, we can all read that. It's in English, and we can understand what I'm going to do. So what am I going to do? I'm going to look at my array of people, pick the shortest person, put them in the output bucket, and then repeat that until I don't have any more people to look at. So that would be, I don't know, maybe Zoe, you first, right? But no, that's cheating. That's not how computers work. I can't just go look at it and say, oh yeah, that's the shortest person. No, I need to go and look at them. So I have to look at you and say, well, I haven't seen all the people yet, so I have to assume that at the moment, Joe is the shortest. So I'm going to say, okay, you're the shortest. So I come here and I compare you and say, okay, now you're shortest. So now you're shortest, you're fine. So now I compare again. Oh, you're shorter. Okay, you're a bit taller. Fine, we're fine, we're fine, we're fine. Okay, you can go first. So, and so on and so forth, right? I'm not going to do the whole thing because it's a bit late. But that would be the process, right? So this is really bad. This is a really bad approach. Who can tell me why?
Keep traversing.
Yeah, I would have to essentially just look at everyone every single time. And that sort of thing of like holding the temporary shortest person is quite an intensive task. So the complexity of this algorithm would land on the exponential. Like this is exponential, so pretty bad algorithm. Let's go to the next one. Okay, so shuffle again or whatever. Okay, so this one is a bit more interesting, but unfortunately equally bad. So bubble sort is essentially has this concept of bubbling up. And then what it's essentially what I have to do is pick a person and then compare that person to the next person and then see if they are in the right order or not. So if they are in the right order, I just leave them as they are and then continue. But if they're not in the right order, I swap them and then continue. And then the condition to stop would be when I go through the whole array and didn't change anyone, which would mean that the array is in order. So I would go here and then, okay, you're fine, you're not fine, so you swap again. So at the moment he's bubbling up, right? So this is why it's called bubble. And then you are fine and you're fine. Okay, so now I reached the end of my array. So now I say, well, did I have to swap someone? Yes, I did. So I need to start again. So this is why this algorithm now is quite bad, because I have to keep going over and over again. This algorithm is bad. Like, it would also fall in the land of exponential complexity. But this one introduces something interesting to think about this algorithm, which is that the order in which sort of how unsorted my input is to start with affects how good my algorithm is going to be. So what would be the worst case scenario for this algorithm in terms of like the initial state of the array? When would I have to do the most operations? Yeah, if it was like completely reversed, because absolutely every single person would have to be bubbled to the right position because they are all in the farthest away they can be from their position. But if my array was fairly sorted and only a couple of people have to bubble up, that would be quite a good algorithm because I wouldn't have to do a lot of passes. So this is sort of introducing the concept of having there's no black or white answers. This is not a bad algorithm every single time. It's a really bad algorithm in certain moments, but it could be decent under different conditions. Next one. There's only 4, so don't worry. Okay, let's try to get a bit better. Let's try to go into a nice algorithm. So now we need to start thinking a bit harder, because we can't just, we need to simplify. Like one of the most important problem-solving techniques is divide and conquer. You need to just start splitting your problem into smaller problems. So what is an easy problem to solve? Well, sorting 2 people is really easy, right? Just like they are there, or this way or this way. So building up on that, sorting 2 lists of already sorted people is also quite easy, because I would just have to compare sort of the first element of each array and then see who's shorter, and then I put that, and then I keep comparing the first 2 items of each list. So we are making some assumptions, and that's something that we have to do in order to get faster. So that's what I'm going to be doing. So this algorithm, what I'm going to do is I'm going to split it in half. So 4 people here and 4 people here. I'm going to keep splitting until I can only have to compare 2 people. So I'm going to split it again and split it again there. And now I'm ready to start comparing. So you guys are OK. So you guys swap. You guys are OK. You guys are OK. So now what I'm going to do is I'm going to sort these 2 lists. So now I'm going to say that, no, that doesn't work yet. I'm not sure that we can do that yet. So what I'm going to do is I'm going to compare the first one from this one and the first one from this one. And because I know that those 2 lists are already sorted, then I know that I can say, OK, so you are definitely shorter than her, so you come first. So take a step out to the front, and then I'll sort them. Sorry. You take a step to the front, and you stay where you were. Sorry, this is easier with computers. So you take a step, and then I would say that you're maybe slightly taller, so you take a step first here, and then you go after him, right? So now this part of my list is already sorted, and then I would do the same with these 2, and then when I'm done with these 2, I would do it with these 2, and then that would be a simpler operation than before. So this algorithm, because it's considerably less complex, and the reason why it's less complex is because by splitting my input every time in half, I'm sort of mitigating the growth of the input, because by splitting something in half, well, you're gaining a lot, right? So that's sort of like the simplified explanation for that. The last one. So this algorithm is, it's not really linear. it lands in between exponential and linear, and that is what's called logarithmic complexity, and it's sort of a curve that sort of lands in between those two. Last one, quicksort. So can you please shuffle again, because you're quite sorted at the moment? So this is the last one. So quicksort. Quicksort is a bit out there, and I'm not gonna explain how I got here, but let's just do it. So quicksort, it depends on picking a pivot. Essentially, a pivot is an item that I pick, and then I'm gonna order everyone that is shorter than the pivot on one side, and then everyone that's taller than the pivot on the right side, and then do the same sort on both sides. So let's say that Joe is a pivot. Now I'm gonna say that everyone who's shorter than Joe go this way, and everyone who's taller goes this way. And this algorithm will sort of keep the original order, so if they sort of automatically sorted, sorry, but yeah, let's try, doesn't matter, no one's gonna check technically, but so now I would do exactly the same, so I would say that maybe Sam is the pivot, and then I would say everyone who's shorter than Sam goes to the left, and everyone who's taller than Sam goes to the right. So yeah, and then I would do the same here. So I would say that Josh is my pivot, and then you two guys are on each side. So now I have, what, 1, 2, 3 pivots, and I have one person here, which is easy to sort. It's one person, so you stay there. You're also easy to sort because it's just one person, cool. So all of this, I know that it's sorted. And then everyone to the right of Sam, then I would have to sort these two. So we've seen that by dividing and conquering, I've made this sort much shorter. So this algorithm also falls into the logarithmic scale complexity. But we also see that both the how out of order things were initially, and also what pivot I pick have a huge influence on how fast this algorithm is. Because if I had picked, for example, Paul as my pivot, and the original sort of, if this was the initial state, I don't know that this array is already sorted. So I have to run my algorithm anyways. So I have to like grab Paul as my pivot, and then I would have to look at this array, and then grab Josh as my pivot, and then look at this array. And that would waste a lot of computing on something that I already, I could have sort of checked before if it was sorted or not. So quicksort, if the input is fairly in order and you don't really pick your pivot correctly, even though quicksort is fairly quick and it's really good, it can be quite bad. So I'm sort of trying to show trade-offs. Okay, so can we get linear with sorting? Can we break this barrier? Can we just like go one pass and just sort everyone? No, can we? Yes, yes or not? So we can, but yeah, so to make an algorithmic omelette, you have to break some algorithmic eggs. And what that means is we have to make trade-offs. We have to make some sacrifices in order to make this happen. So the sacrifice that I'm gonna make here is that I'm going to say that what happens if I don't really care that much how fine-grained my sort is? What happens if I only want to have maybe 3 buckets of people, one of maybe short people, people of medium stature, and people that are really tall? And maybe that's enough. And maybe I have some process later on that will sort those buckets if needed, and I don't have to waste a lot of computing in like very fine-grained sorting. So that would approach linear sorting, because what I would do is I would say, well, I'm going to divide people in 3 categories, and I'm going to just go one by one and say, okay, you are going to be on group 1, you're going to be on group 2, you're going to be on group 3, and I just do one pass of my array, and that's linear, right? So what I'm trying to show here is that by making assumptions, by reducing the constraints of our problem, and by just making some trade-offs, we can get a lot faster if we need to. But here, picking the right buckets becomes the key skill here. It's the most important thing. So thank you to my volunteers. You can sit down if you want. Thank you. But yeah, sort of, Joe did this, and I love talks that do this, that I talk about something, but why would we do that? Why do we care about sorting? What do we gain by sorting stuff? Why would we want to sort in the first place? why do we sort stuff? What's the purpose of putting things in order?
Easy to read.
Yes, it's easy to find stuff, right? It's the stuff that I told you to remember from Google, because the reason why Google is so quick at finding stuff is because it's really good at sorting stuff so that when it's going to find them, they're there. So, absolutely. So, sort enables search. They're sort of like both sides of the same coin. So, we sort things when we want to find them quickly. So, deciding if you even want to sort your data is actually the first trade-off that you have to make. It's the first decision that you have to make is, do I even want to sort? Do I even need this data in order? So 2 examples here. If finding things in my messy bedroom is not too hard, why would I bother tidying my room up, mom? So I finally have like a scientific answer to why I didn't tidy up my room. It's because I have a method to my chaos. It wasn't too hard for me to find things there. So it wasn't worth for me the time that I would spend sorting stuff up. It's gonna get out of order pretty fast and I would be wasting a lot of computing power. So, but if finding things quickly is more important to you, then maybe you should consider sorting small amount of stuff and often, rather than sorting big, like large amounts of stuff once. So those are sort of trade-offs that I'm offering. So yeah, to conclude, things that I would extract out of this. So thinking about trade-offs is at the very core of what you do, of what we do as programmers. So it's something that I'm trying to force myself to think more and more about. Something that I think if I been teaching at Northcoders when you were a student, you may have heard me say that I always recommend you to approach solving problems as if you had like, I don't know, pieces of paper in front of you or little balls that you have to put in different boxes, stuff like that. Why do I ask you to do that? Well, because you already have a lot of intuitions built in around how to manipulate things efficiently. Like you know how to put papers into different folders or sort your books alphabetically. And all of those things apply and transfer to programming. So I encourage you to do that more and more because it really transfers. And you've seen how easy it was. Well, fairly easy to understand fairly complex algorithms by just like doing what you would do if you needed to sort people by height. And then the last thing that I would recommend you to do is to develop the ability to communicate ideas, technical ideas, effectively at different levels of abstraction and complexity, because that will definitely get you jobs and promotions if you're already on a job. These are skills that being able not only to communicate to programmers in your team that have different levels of understanding, but also to communicate to members of your company, but they might not be programmers, or maybe to clients that they are interested in your product, but they are not programmers. Being able to explain these ideas effectively, those are skills that really will get you a job and will make you stand out in a company. So yeah, I have to leave you with that. Thank you.